we're going to talk about Floquet fields.
Okay, first I would like to thank Dr. Mark J. Hadley for giving me the inspiration for this work with his published paper in 2017, where he derived electromagnetism from the twisting of the U1 bundle from general relativity. And I'd also like to thank Dr. Prasanta Pal, one of my past co-authors in neuroimaging in 2017, for his work in quasi-one-dimensional dynamics with Class C systems. And I'd also like to thank Rudon for giving this work a room. Yeah, thank you again. These are numbers with IonQ Forte noise class models baked in, fidelity plateaus above 0.96 after 5,000 periods. The spiral doesn't fight decoherence, it routes around it. It's cheaper than the night of beers in Singapore. This is part of my home build. The board defaults to 0.4 Teslas per meter. It's kind of like a sledgehammer approach. If I tune the voltage down, I can target a lower static phase gradient, which would be more appropriate for certain atoms and ions. The proposal is not new hardware. Maybe less, actually. It's using spatial phase structure as the control resource instead of canceling it. The imaginary part isn't magic, it's geometry. The ion's position naturally computes the phase shift. As Dr. Mark Hadley pointed out to me in private correspondence, the field has a long history of conveniently overlooking non-scalar terms when it suits them. If imaginary coefficients make Hamiltonians unphysical, then so much to tell the weak interaction has been breaking unitary since breaking parity since Wu 57. As you can see, this is the evolution of the phase within the static field gradient over time within the Floquet cycle. Normally, in, say, ions, trapped ion hardware, they try to zero out this phase front. So basically, instead of naturally inside of the background, you just have natural curvature. They try to zero it out. X heavy, 3x3, 50 periods, and fidelity plateaus at classical noise. No, too sensible. We need $1 million fridge that barely works. Most quantum hardware is designed around protecting states. What I'm going to show you is a regime where we don't protect the state at all. We stabilize the orbit. If the orbit is stable, logical information rides the orbit. You don't need to error correct the state. The dynamics do that for you. Think of pi over 512 as the pitch of the spiral, not the height of the walls. On the right, big expensive walls that have zero pitch. Side flip, magnitude tiny, true symmetry of the orbit. If this were just noise, it wouldn't care which way I flip the qubit. Pivot. Nature already does phase-mediated attractor dynamics better. Solar wind, HMI sun, AIO171 angstroms, so on and so on. In the corona, we see a Lipinov exponent of negative 4.8 on 4 stiff axes. This isn't just stability, this is structural locking. Across each physical system observation, I measure how much the trajectory changes at each moment. Sharp changes, I classify those as turning events. PCA reveals which directions the system explores freely and which are locked down. The stiff axes, this is where the system is structurally constrained. On each stiff axis, I measure contraction. Negative values mean the system is being pulled back in, attractor behavior. I spent a year asking DTC theorists and experimentalists what I was seeing with my sims, because at first, I had no idea. I got silence. I put the preprint for 171 angstroms on Zenodo, and within 3 days, over New Year's, I had Lockheed Martin Astrophysics Laboratory helping me optimize my data pipeline. I took the hint from Dr. Capasso. If phase is the primary degree of freedom in optics, why simulate 1.5 terabytes when I can ride 100 kilobytes of phase? Now for the boring application. Maybe why some of you are here. Shore-like purity finding on a 17-bit coprime demonstrated 20 logical qubits on as far as 4 physical spins. This won't fit in the RAM of your laptop simulators, yet this used less than 2 megabytes of RAM on one CPU. Why not? Because we're so focused on tracking state vectors, which don't explore Hilbert space freely. This is second-order Suzuki-Trotter split operator method on a 3x3 lattice. If you measure global magnetization, look for the sharp FFPT. That will be your attractor signature. Half-life of autocorrelation tells you how robust it is. Even a 3x3 lattice shows it. You don't need 100 physical qubits. As you scale up, you converge to mean field on the result I showed on slide 8. We don't need $1 million fridge to stabilize the orbit, but we might need real signal processing to read it out. The line width is set by the stability of the driven orbit, not by bare SO3 precession. If the orbit is stiff, the spectrum is sharp, and if the spectrum is sharp, the qubits separate themselves. I move the difficulty from cryogenics to demodulation. Everything's open, GPLB3, fork it, extended, cite Jakarta. If you have a free AWU channel open and you're tired of fighting noise, let's grab a coffee or beer. Thank you.